Well, we can start, and we very much hope you will enjoy this workshop. So our first speaker is Stefano Antonini from the University of Maryland. And he's going to tell us about slicing duality and holographic cosmology.
Okay.
And if you want to ask questions, raise your hands, and we will lend you the microphone.
Okay. Hi, everyone. Thank you to the organizer for organizing this nice workshop and for inviting me to give a talk. And I'll be talking about some work that I did with Brian, my advisor, and Mark Van Ramsdonk, his student, Padar Simija. And most of what I'll be talking about is published already in this paper. And another paper will probably come out soon, this month or next month, with a follow-up with some features of these models. So the talk will be divided in 3 parts. After introduction, probably half of the talk I'll spend describing how you can introduce cosmology in a DSCFT using this approach. And then I will talk about some specific features of these cosmologies and how you can reconstruct them given the microscopic theory. So since I'm the first speaker, I figured that I should give my 1-slide imprecise review of a DSCFT correspondence. And so a DSCFT, as we all know, it describes a theory of gravity, quantum gravity, in d+1 dimensions in some asymptotically ideal spacetime, in terms of a conformal field theory with 1 dimension less, living on the boundary of this spacetime. Now, a DSCFT gave us a lot of very interesting insight into quantum gravity, told us many things that we didn't know about quantum gravity. But one thing that at the moment still is not clear how to do is how to describe cosmology within a DSCFT correspondence. So there are different approaches. All of them have pros and cons. The approach I'm gonna be describing today is one that Mark Van Ramsdonk introduced a couple of years ago, and then I and Mark have been working on since. So the question we want to answer is, how can we obtain a fully macroscopic description of cosmology in terms of some dual theory? And if we get this kind of cosmology, then what kind of cosmology would that be? So what eras would we have, or how can we probe it, starting from this microscopic theory dual to it? So given that what we are working on is a DSCFT, it seems natural as a first step, at least, to focus on negative lambda cosmologies. So these cosmologies generally regarded as disfavor from an observational point of view, because we observe an accelerated expansion in our universe. And that accelerated expansion is frequently described in the simplest possible way with a positive cosmological constant. There are other possibilities to describe it, which are, for example, quintessence models. I will mention that at the end. But regardless or not of whether these specific cosmologies can describe our own universe, it seems like a very interesting first starting point to describe cosmology within a DSCFT. Now, the fact that we have a negative lambda doesn't mean that it's easy to describe cosmology in a DSCFT. And I think the simplest possible way to see that is that if we have these cosmologies, which are generally Big Bang, Big Crunch cosmologies, there is no asymptotic boundaries where to define a dual CFT. So we cannot just use some extrapolate dictionary or the usual tools that we have in a DSCFT to describe this cosmology holographically. So the idea is that in these specific models of cosmology, you can have some asymptotic boundaries, asymptotically ADS regions, if you consider a complexified geometry associated with this cosmology. And so we will use this feature. So we will use the fact that in a complexified version of the cosmology, you have asymptotic boundaries to define a holographic dual on these asymptotic boundaries. Now, before going into the details of the models, let me mention that the first time it was noted, as far as I know, that cosmologies, FRW cosmologies, which are symmetric, have a dual with asymptotic boundaries, have a space-time, a complex space-time associated to it with asymptotic boundaries, which are ADS, was Maldacena and Mao's paper in 2004, where they noticed that if you take a symmetric Big Bang to Big Crunch cosmology, and you analytically continue the scale factor, what you get is a Euclidean wormhole, which is asymptotically ADS with two asymptotic ADS regions. One simple example of that is taking just an FRW metric driven by radiation and a negative cosmological constant. And in that case, you can solve Friedman equations analytically, get a scale factor, which is periodic. So you have a Big Bang and then a Big Crunch. And if you analytically continue the scale factor, you get a spacetime, Euclidean spacetime, which has two asymptotic boundaries at plus and minus infinity, which have the correct ADS asymptotics. So this was the first case where this was observed, and we use this kind of idea to construct our macroscopic duals living on the boundaries of this complexified geometry. So is there any question about this first introduction? Okay, so let's dive into what we've done in these last few years and months. So I will start by talking about only the microscopic construction, so not gravity for the first few slides. It's only the boundary theory. And the boundary theory we consider is two copies of a holographic 3D CFTs. So there will be an asymptotically ADS spacetime associated to each one of these 3D CFTs. And then we consider a 4-dimensional CFT, which can in principle be holographic, but it doesn't need to be. And in general, it won't be. And this 4-dimensional CFT lives on R3 times a finite interval. Now, one feature that we want from this 4D CFT is that we want it to have many less degrees of freedom than a 3D theory. An idea to understand that, the intuition is that we don't want this theory to modify very, very much the behavior of the 3D CFTs because we want to retain a 4-dimensional dual description. So we don't want this theory to have a lot of too much influence, at least in the UV, on the 3D CFT duals. And again, since we want these UV asymptotics to be ADS in the duals, we want to couple this 4D CFT to the 3D CFTs using a relevant perturbation. And the way we do this is to take the two 3D CFTs and coupling them at the end of the interval, at the two ends of the interval. So now the two 3D CFTs will be interacting, and the interaction will be mediated by this 4D theory on the interval. So this is the picture we should have in mind, where we have two 3-dimensional CFTs, and then a 4-dimensional CFT on the interval coupling them. Now, in this case, we will have coming out, let's say from these 3D CFTs, we will have two ADS for spacetimes. And these degrees of freedom are generally not holographic. Now, we know that if we have a Euclidean path integral, so some Euclidean theory, we can slice open the corresponding path integral to define some state, and then an associated Lorentzian theory. Now, the theories we're interested in are theories that have two reflection symmetries. One is the reflection symmetry along the interval, and another one is a reflection symmetry along one of their three directions. This means that we have two different natural ways to slice open this path integral. And the two different ways will define two different states, and in general, two different Lorentzian theories. So now, before introducing holography, let's see in the boundary theories what these two different slicing give rise to. So the first one, I will try to keep a consistent color scheme because we have a lot of different models here. So I'll try to always have a blue for the first slicing, a yellow for the second slicing, and red for the Euclidean. So in this first slicing, we are slicing open, cutting in half the interval. And so we use this first reflection symmetry to define a time symmetric state. And if we slice it open this way, what we get is an excited state of the 4D CFT only. So let me point out here that there is no 3D degrees of freedom in the corresponding Lorentzian theory, because the initial state we use to evolve the Lorentzian theory only has 4D degrees of freedom along their three directions, because this cut doesn't intersect in any way the 3-dimensional CFTs. And note also that it's an excited state. And the way to see that is that we only have a finite amount of Euclidean time evolution before we slice open the path integral. And that in general defines a an excited state of the corresponding Lorentzian theory. The other slicing is the, let's say, the most intuitive one, is the one that just defines the Lorentzian theory corresponding to the Euclidean theory we have initially. So it's a slicing that cuts in half one of their three directions, so the one perpendicular to the interval. And in that case, what we get is again a 3D CFT, and a 4D CFT coupling them in the middle in Lorentzian signature. So we promote one of the three directions to be the time, just like we usually do in quantum field theory. Now, in the theories we are interested in, this theory on the interval and the corresponding Euclidean theories will not be a CFT in general. It will be some theory with a mass gap, because it's just a theory in an interval coupled to 3D theories. It's, in general, we don't have that doesn't result in a CFT. And in the case we're interested in, it does not result in a CFT. Note that this is a vacuum state, because this direction along which we are slicing open the path interval, it's an infinite direction. So we have an infinite amount of Euclidean evolution before slicing open the path interval, and that defines a vacuum state. So this is the macroscopic setup we have. And if there's any question before going to the holographic part, please go ahead. Otherwise, I'll describe the holographic setup. Okay, so we have this microscopic theory and these two possible slicings. And now let's try to introduce the holographic dual bulks of these two theories. We can start from the Euclidean picture, where we had this Euclidean sandwich theory with two 3D CFTs coupled by a 4D CFT. And the dual of that has two possibilities. The reason for that is that this theory has a scale, the microscopic theory, given by the length of this interval. And this means that in the IR, it flows to a 3D theory. This 3D theory in the IR can either be a CFT, so gapless, or it can be a gap theory. So in the first case, if it's a gapless theory, so we have an IR fixed point in the RG flow, then the idea is that you can have non-trivial physics to arbitrary love wavelengths because you have no mass gap. And that in the dual would correspond to have the two ADS for spacetimes just going arbitrarily deep into the bulk. We just have a complete bulk spacetime dual to each one of the two 3D CFTs. Note that the two asymptotic boundaries to which this ADS for asymptote 2 are also coupled by non-gravitational degrees of freedom, which correspond to those for the auxiliary degrees of freedom that we use to couple the two CFTs. So this is one possibility, and it's not the one we are interested in. The one we're interested in is the case where in the IR, this sandwich theory flows to some gap theory. In that case, the interpretation of this gap holographically would be to have some IR cutoff into the bulk. And this IR cutoff can be introduced in many different ways. One possibility has been studied in the literature is, for example, putting end of the warp brain to cut off the IR. This is something that is being used also, I think, in the early days of ADS QCD to describe this kind of holographic models of QCD. And in our specific case, we also have, another possibility to cut off the bulk deep into the IR is to have the two ADS for spacetimes that are dual to the two 3D CFTs to join up deep into the bulk. This introduces a natural cutoff in the sense that this wormhole, it will be a Euclidean wormhole that just has two asymptotic boundaries, and so you cannot go arbitrarily deep into the IR. So this is another possibility for how to introduce an IR cutoff in the bulk. And this is the theories we're interested in. So theories that once you couple them, they flow in the IR to a gap theory whose dual is given by Euclidean wormhole. I will give some more intuition about how these kind of setups could arise using W holographic setup in the next slide. So before doing that, let me just mention two features. Once again, I want to remark the fact that here we not only have this Euclidean wormhole in the dual theory, but we also have non-gravitational degrees of freedom coupling the two asymptotic boundaries of the wormhole. And that's the leftover of the four-dimensional CFT that was coupling the two 3D CFTs. Another fact is just saying that for this Euclidean wormhole, the metric will be conformally flat, and this conformal factor will have two poles, two simple poles at the two asymptotic boundaries. Okay, just to get some more intuition about this gap case and why we should have a Euclidean wormhole, let's consider a specific case where the 4D degrees of freedom that we use to couple the two 3D theories are also holographic. So this means that we have a 5-dimensional bulk, and the 5-dimensional bulk will also have an end of the warp brane, which corresponds to the dual of the 3D CFTs. So this is a setup similar to the ones for the ones of you familiar with it, to the ADS BCFT setups that Tagayanagi and collaborators studied, where you have a conformal theory with a boundary. The corresponding holographic dual will be a bulk ADS with an end of the warp brane cutting off this bulk. Now, in our case, where this theory confines in the IR, again, the idea is that you have this ADS5 bulk that must be cut off somehow in the IR. And one way to cut off in the IR this bulk is to have the two branes corresponding to the two boundaries of the boundary theory to join up deep into the bulk. Now, what before was the Euclidean wormhole in 4 dimension is what this brane is here. So this brane will have this, the metric of a Euclidean wormhole. And our claim is that if you don't have a holographic set of degrees of freedom on this interval, so if you don't have this ADS5 bulk, the corresponding wormhole will still be there. So using these holographic setups is more intuitive to understand the wormhole because you just have a brane in the bulk which connects deep into the AR. But if you don't have the holographic setup, the idea is that still you can have some connected spacetime that gives you a natural cutoff and builds up this wormhole. Okay, so now we have our Euclidean dual. The Euclidean dual is given by this 4-dimensional wormhole with some non-holographic degrees of freedom coupling the two boundaries. And we saw that in the microscopic case, we had two different slicing of the corresponding path integral corresponding to two different Lorentzian theories. So now we want to understand what are the corresponding Lorentzian gravity theories associated with that, the Lorentzian duals. So for the first case, that for DCFT excited state, that corresponds to a symmetric Big Bang Big Crunch cosmology. And a way to see that is that if you take this Euclidean wormhole, slice open, noting that this is actually, let me mention two things. First, this is not really some SN or S3. This is actually R3, so it's planar, the boundary. I just didn't know how to draw that. And also let me mention that here you have the auxiliary degrees of freedom coupling the two boundaries that I'm suppressing in these pictures because I only want to look at the bulk dual, which is gravitational. Now, to analytically continue this Euclidean path integral saddle in the bulk, which corresponds to the Euclidean path integral of the macroscopic theory, what you want to do is take the slice along the time symmetric slice, and then analytically continue that and use that as the initial data in order to define the Lorentzian theory. If you do that, what you get is a symmetric Big Bang Big Crunch cosmology with a spatially flat FRW metric. This is not exactly what Maldacena and Maus were doing. So that slide that I showed at the beginning showed that if you have a cosmology and then you analytically continue, you get a Euclidean wormhole. So here we're doing the same things the other way around. So this is one possible slicing. And the other one, the one that defined the vacuum state of this 3D 4D 3D theory. So we have this gap Lorentzian theory, which is just the Lorentzian version of the Euclidean sandwich theory. And that corresponds in the bulk dual to a static planar traversable wormhole, so an eternally traversable wormhole in ADS. And this wormhole has a planar cross-section. The way to see that is, again, take the Euclidean wormhole, slice it open, cutting in half one of their three directions, analytically continue, and this just corresponds essentially to take your metric and choose one of their three directions to become the time. And in that case, you get the exact same metric, and the scale factor still has two simple poles corresponding to the two asymptotic boundaries. So in this case, you have this eternal traversable wormhole. So that's a great question, because planar wormholes require large amount of negative energy to be sustained? So this is a very good question, and you definitely need to study in detail bulk effective field theory models that study this, that allow to support these metrics. And this is something that we're actually doing now. There is an example by Mark and Alex May, and I think Peter too, that they studied these models where they consider 4D CFTs in the bulk coupled to some 4D CFT in the interval, so something similar to what we saw before. And they study holographic models, and they model the interface between these two. Okay. If you model the interfaces holographically using end-of-the-world brains, they show that you can have a very large amount of enhanced negative energy in these setups. But you're completely right that you need to have some very specific physics going on there, some like large amount of Casimir energy in order to sustain this wormhole. And we're assuming that such solutions exist, and we're working under that assumption. But that assumption is something that we are working on. So it's not, we don't have a microscopic specific example to show it yet.
Yeah, so I'm a little bit confused about the case where you take a large N CFT in 3D and you take a non-holographic QFT with small central charge in the interval, and then you take the large N limit.
Sorry, and then?
And then you take the large N limit of the big CFT, of the 3D CFT. In that case, I would imagine that the back reaction of the 4D QFT would be small as long as we're near the boundary, right?
Yeah.
So the point where this wormhole geometry has a minimal size, the depth in Z, does it scale with some factor of N? And if so, is the curvature finite there, or is it?
Well, the idea is that the ADS length that sets the length of this wormhole, the length of this wormhole will be set by some relationship between the 3D CFTs,
yes,
large N, and the 4D CFT, large N. In general, the idea is that the reason why you have this Euclidean wormhole is because the coupling between the two 3D CFTs is generated by a 4D CFT coupled to it, which is coupled by relevant perturbation. So it doesn't affect at all the UV, but it does affect the IR, and in particular generates a lot of entanglement between the two 3D CFTs such that you can have a connected space.
Yeah, but the amount of flow you have to undergo scales with N or not?
Scales with N of...
I mean, if you keep the 4D QFT fixed, then you take the larger limit of the 3D QFT.
Yeah, I guess you can also take both QFTs to have a larger limit, just with two larger limits, one much larger than the other one. And that case is the one that you can understand more simply using, I guess, double holography. And in this case where the degrees of freedom are non-holographic, I think that you also need, yeah, I think that the depth should scale with N, and so you need to have a very, very long RG flow.
Okay, but in that case, do we know if the curvature will be finite everywhere, or?
In this case, yes, we would expect the curvature to always be set by the 3D CFT large N limit.
Okay, thank you.
So yeah, basically to answer, I think if understood what your question was really asking is what you were aiming at, I think the idea is the curvature of this traversable wormhole is always small, so you can use an effective field theory description in the wormhole in order to describe the physics. Alicia, were you asking a question? Oh, okay. So we saw a lot of different models, so I wanted to give a quick recap of what we have so far. So we started with this Euclidean theory, which microscopically it's a Euclidean sandwich theory, two 3D CFTs coupled by a 4D CFT. And this theory is gapped in the IR, and it corresponds to having a Euclidean wormhole in the bulk with the two asymptotic boundaries coupled by non-gravitational degrees of freedom, which are essentially associated with the auxiliary for the degrees of freedom that you use to couple the two 3D CFTs. Then in these models where you have two reflection symmetries, we can slice open the path in two different ways. One way gives you a 4D CFT excited state where you have no 3D degrees of freedom, and that corresponds to having a cosmology in the bulk. And the other possibility is to slice it open just to define the corresponding sandwich theory in Lorentzian signature. And this vacuum of this gap theory will be dual to a Lorentzian traversable wormhole. So note now that this cosmology and this ADS traversable wormhole, or equivalently for this FT excited state and the gap theory vacuum state, are related to each other by this double analytic continuation. And they both arise, are independent theories, they both arise from the same Euclidean path integral. And this is what we call slicing duality. The idea is that we have these two theories, Lorentzian theories, which are different theories, different states, but they both arise from the same Euclidean path integral. And in this sense, they're related to each other, and they can be used to study each other, as we will see in the rest of the talk. Okay, is there any other question about this first part before I move on to the consequences for the cosmology? Okay, so now we have an idea what this slicing duality is. Let's try to understand how to reconstruct this cosmology from the dual microscopic theory, and also what kind of properties this cosmology has. So the first thing I want to go back to, which I neglected before, was the fact that we have this auxiliary system in the bulk effective path integral. We had our wormhole, the Euclidean case, but we also had some auxiliary system coupling the two boundaries. So if you actually slice open the path integral carefully along this symmetric slice, you not only get a cosmology. Okay, let's start with this B slicing, which corresponds to the cosmology slicing. So if you slice open here the Euclidean wormhole, you get this cosmology, but at the same time, you're also slicing open your path, your auxiliary non-gravitational system coupling the two boundaries. So this means that you define a cosmology entangled with a non-gravitational path on Minkowski spacetime. Why it is entangled? Because intuitively, because here this is essentially a thermofield double, a Euclidean path integral preparing a thermofield double state between degrees of freedom in the cosmology and degrees of freedom in this path. So you get a separated path entangled with your cosmology. And this already tells you that probing the cosmology is not something particularly obvious to do in a DSCFT because you don't have any asymptotic boundary. Actually, this cosmology is dual to a state, excited state of these degrees of freedom, which are completely disconnected from the cosmology. So it's not really clear how you can use, for example, extrapolate dictionary to probe this cosmology. On the other hand, if you look at so this is the first case with an entangled path. If you look instead at the Euclidean wormhole and you slice it along this A slice, which corresponds to the Lorentzian traversable wormhole, what you get is that you not only have the traversable wormhole, but you also have a path coupling the two boundaries. And this is actually something that we would expect, because we know that if you have a traversable wormhole, you must have some coupling between the two asymptotic boundaries. And this coupling is not, in this case, some local direct coupling, it's some coupling mediated by these auxiliary degrees of freedom. Okay, now that we have this picture in mind, we can think of why this slicing duality is useful at all. Well, this slicing duality can help us to probe this cosmology, which is our goal, using a DSCFT in a much simpler way that you would expect. And the way to see this is that, while as we saw just now, the cosmology is encoded in a very hard way in this 4D CFT excited state. I will also mention another way to understand that in a second, but essentially the fact that you have these two disconnected spacetimes already tells you that you have something which is not ordinary DSCFT. And in particular, this cosmology is essentially an entanglement island for the auxiliary path. And I will mention islands at the end if I have time. And then the wormhole case, on the other hand, is much simpler. The reason why it's simpler is because you just have a traversable wormhole with two asymptotic boundaries, and that's where the dual theory lives. So you just can use some normal ADS-CFT dictionary, some extrapolate dictionary to probe your wormhole from the microscopic dual theory. You have a question? Oh, okay, sorry. No. I thought he was raising his hand. So in the macroscopic dual theory, it's much easier to probe the wormhole than to probe the cosmology. But that's where the slicing duality comes into play, because we know that these two theories are equivalent and related to each other by double analytic continuation. So if you want to probe something in the cosmology, the idea is that you can use the normal ADS-CFT dictionary, probe the wormhole, then analytically continue the observable to probe the cosmology. And that's much simpler than using some very, very hard to use dictionary for the cosmology directly. So in this case, for example, for the cosmology, you will need to use very, very complicated operators, expectation value of extremely complicated operator, very complex operations to do on the macroscopic state in order to get information on the cosmology. By using the wormhole and then analytically continuing, simplifies your life a lot. So I just want to make clear a little bit more, relying again on this double holography, why probing the cosmology is hard. And the idea is that the excited state looks thermal. It's a very, it's a highly excited CFT state. So we can think of it as a Euclidean black hole, as a black hole. And in particular, if you consider this Euclidean black hole with an end-of-the-world brane, as we saw before, and then you slice open these to define your Lorentzian state, what you get is a double-sided black hole, where the 4D CFT, whose excited state describes the space-time, lives on the right asymptotic boundary. And the brane, which is what hosts the cosmology, this is a brane world cosmology, lives in the left asymptotic region. So the idea here is that if you want to probe the cosmology directly from the 4D CFT excited state, you need to use some observables that can see behind the horizon of the black hole. And we know that that's something very, very hard to do. These models were originally studied by Brian and Mark and collaborators. And then by Brian and me, there was a follow-up about this. And so looking behind the horizon of a black hole, it's a hard task. It's you have to deal with Python slanches to use some more modern language about complexity of these operations. So this is clearly a very hard thing to do. But on the other hand, if you look at the wormhole picture, in this double holography, that would just look like pure ADS with an end-of-the-world brane. So if you want to probe this brane, which is the wormhole, you can just use extrapolate dictionary and relate it to the microscopic theory on the boundary. In particular, reconstructing a wormhole is really quite easy. This is what we've been doing in the last few months, and the paper will appear probably this month or next month. There are many different ways we can probe it. In particular, here we showed that if you have a bulk scalar field in this traversable wormhole geometry, that corresponds to, in the dual confining theory, corresponds to a spectrum of massive particles. If you have two different scalar fields with two different masses, you will have two spectra of massive particles. Given this information, you don't need anything else to reconstruct your wormhole. Given that, you can reconstruct the geometry completely. And we built a complete algorithm to do that just by taking two spectra and then reconstructing the wormhole out of them. And in fact, this is a numeric implementation of that algorithm. And you see that we just picked some form of the scale factor, no particular physical meaning, and consider the spectra associated with that scale factor by quantizing two scalar fields, and then reconstructing from this spectra the corresponding scale factor. And here the two lines are almost completely superimposed, so you cannot really tell the difference between the two, but they're both there. And so this clearly shows that a simple observable such as the spectrum of particles in a confining theory already tells you everything you need to know about the wormhole scale factor. And there is also other observables doing that. For example, heavy correlators in these dual theories are enough to reconstruct the wormhole geometry. Once you have the wormhole geometry, you analytically continue it, and you get the cosmological geometry, the cosmological universe, so the cosmological scale factor. So this is an example of how reconstructing the wormhole is not hard, and you can use then analytic continuation and this slicing duality to reconstruct the cosmology from the microscopic theory. Now, let me mention a few characteristics of these cosmologies. In particular, we saw that we are defining a cosmology, but we're also defining a specific state for this cosmology, because we're slicing the path integral on some time symmetric slice, and that slice, which corresponds to the time symmetric slice of the cosmology, so at the end of the expansion, in the beginning of the contraction, that slice hosts the initial state for the cosmology. So we are actually defining the state for the cosmology at late times. This is analogous to Hartle-Hawking, except we do have boundaries in our Euclidean past. One ADS boundary in the Euclidean past in the path integral. So we have a state at late times. And in this sense, the cosmological evolution from this purely quantum point of view is better understood as being forward towards the Big Crunch and backwards towards the Big Bang, starting from the central point. The initial state is actually in the middle, so at the end of the expansion. And this fact actually is useful to solve some naturalness problems of cosmology without the need of inflation. Of course, inflation can solve them all. And I'm not saying that in our models we don't need inflation. I will comment about that later. It might be that we don't need inflation, but at least for some of the naturalness problems, we might not need inflation. Flatness, okay, flatness is the easiest. It's just built in because the macroscopic theory is on R3. And so we just have a spatially flat Friedman universe. So the flatness problem doesn't arise at all in this case. Another interesting thing is cosmic coincidence. Cosmic coincidence is the fact that cosmological constant and the rest of the energy density of the universe right now are of the same order of magnitude. And this is quite a coincidence considering that the cosmological constant is constant during the evolution of the universe, while the rest of the energy density scales with different powers of the scale factor. So the fact that they are of the same order of magnitude now is a very big coincidence. In these Big Bang Big Crunch models, not only ours, but in general, this problem is generally avoided because at the time symmetric point, they must be equal in order to give rise to this turning point. And at that turning point, you have only one scale, which is the scale of the cosmological constant that sets both the time variation scale of the energy density and the age of the universe, meaning that if you don't go too far back towards the Big Bang, cosmological constant and energy density will be of the rest of the energy density will be of the same order of magnitude for most of the evolution. And finally, the last one, and also particularly interesting one maybe, is the horizon problem. So the horizon problem is that if you look at the CMB and you look at points that are very far from each other and never been in contact before you hit the singularity, if you hold them back in time, they are highly correlated. So it seems strange that if you never had causal contact between 2 points, you have a correlated state. Now, let's see how horizon problem could not arise in our case. The idea is that the cosmology and the wormhole geometries are related by this double analytic continuation, and in general, all the observables, and not only the scale factor, not only the metric, are related to each other by double analytic continuation. The simplest example of that is to take the codimension 2 slice at the center of the wormhole at time equals 0, or at the center of the evolution in cosmology. And if you look at that codimension 2 slice, observables in the cosmology are exactly equal to the corresponding observable in the wormhole. Now, this feature tells us that if in the wormhole you have correlation at very long scales, then that correlation will also be in the cosmology. Now, in the wormhole, you do have these correlations. And the reason for that is that in the wormhole, you have a vacuum state. And you could argue, okay, but this theory is confining, so maybe we don't have correlations along scales anyway. Actually, we found out that there is a massless sector associated, for example, with Goldstone bosons of some internal symmetry breaking. Anyway, you have a massless sector in this wormhole theory and in the corresponding microscopic theory. And so you have, being a vacuum state, correlation at arbitrary long wavelengths. And this correlation is naturally inherited by the cosmology. Now, this would mean that the reason why we have these large scale correlations is just that the Euclidean path integral that prepares the state just builds in the cosmology such correlations. So the state of the cosmology is defined by Euclidean path integral that naturally introduces these correlations on large scales. Okay, here I just wanted to point out a feature, which is given a microscopic setup, so 2 3D CFTs and 4D CFT and the coupling between them, that completely defines the model and completely defines also the holographic dual and the corresponding cosmology. Now, in particular, as we were saying before, effective field theory, as long as you are far from the cosmological singularity, can describe these models. And this means that semi-classical Einstein's equations hold and describe the dynamics in the bulk. And in particular, the expectation value of the stress tensor that appears in these semi-classical Einstein's equations is just the expectation value in a non-vacuum state in the cosmology. It will be just some state where you have radiation, you have matter, you have many different things. But we saw that the wormhole is a vacuum state. So that expectation value is a VAV in the wormhole picture. Meaning, since the two expectation values are related to each other by double line continuation, this means that whatever content you have in your cosmology must arise from some kind of vacuum energy in the wormhole. And this is an interesting feature that tells you that whatever you have in the cosmology must necessarily correspond to some specific vacuum energy in the wormhole. This is really something surprising somehow. And that's the reason why we call this paper Cosmology from the Vacuum, because the vacuum energy of the wormhole completely defines whatever goes on in your cosmological universe. Okay, one last thing I want to mention before concluding is that if we want to really try and describe, of course, here we are making a statement about some theoretical facts in these negative lambda cosmologies. But if we want to make them somehow realistic and describe our own universe with them, we have to, of course, account for a lot of different things. One of them is definitely an accelerated expansion, because these cosmologies are Big Bang, Big Crunch cosmologies with a negative cosmological constant. But we see from observations that our universe is expanding with an accelerating rate. And the simplest way to describe that is a positive cosmological constant. It's not the only one. There are other models like quintessence. So if you have this time-varying scalar field, then they can describe a phase of accelerated expansion in a universe, even if there's a negative cosmological constant. So the question we want to answer here is, can we have an accelerated expansion phase in these negative lambda cosmologies? Because we not only need usual quintessence models, we need to be careful, because whatever matter content you put in the cosmology affects the wormhole too. So we want that we want to have an accelerated expansion, but we want to preserve the existence of the wormhole and to have a well-defined dual theory. Particularly, the scalar field must satisfy, for example, the BF bound. Otherwise, you wouldn't have a well-defined dual CFT or a well-defined wormhole either. So as a first step towards the real cosmology, we've been trying to work on it. This is still a work in progress. And the idea is that if we take a scalar field with radiation and a negative cosmological constant and build a cosmological model out of it and try to study its equations of motion, the scalar field must be in some classical potential. And the question we're asking is, first, can we have an accelerated expansion? Second, does that model also preserve the existence of the wormhole? Third, can we also have a well-defined dual theory? So does, for example, the scalar field satisfy the BF bound? Now, for the simplest choice, and the reason why this is the simplest choice, I won't go into it, but I'd be happy to talk about it after the talk, that we have is the Higgs potential, so just a quartic potential. And for these potentials, we can get accelerated cosmological solutions. We can get a wormhole, but the scalar field must violate the BF bound. So this means that the wormhole theory is not really well defined. It's not stable. So this seemed pretty concerning. Then we started looking at different potentials, and we found out that if you just take, for example, an exponential potential for the scalar field, which is something frequently used also in inflationary scenarios, you can get accelerated expansion, a wormhole, and also satisfy the BF bound. Generally, these accelerations for the specific potentials we looked at are short. And so an open question is, how long of an expansion can you get without violating the BF bound or without losing the existence of the wormhole? Okay. Before concluding and taking question, I'd like to make a side comment about cosmological islands, since Liz will also be talking about them soon. In this case, I will talk mostly about the region modeled by Harman and collaborators, because they study flat, spatially flat cosmological universes, which is the case of our interest. And in this case, what they find is that if you take this spatially flat Big Bang Big Crunch cosmology, you take a large region at the time symmetric point. These large regions satisfy a set of necessary conditions to be islands, entanglement islands. And if, and then what they do is to consider a bath, a non-gravitational bath, entangle it with radiation in the cosmology, and show that large regions of the bath, if you want to compute entanglement entropy of large regions of the bath, they will have islands in the cosmology. Now, our models are exactly the same. So they don't add anything to this specific analysis. What they tell you is, well, there is actually a bath that you don't need to put in by hand, because we saw that in the cosmology slicing, you get a cosmological universe entangled with a non-gravitational bath. This is what the path integral is telling you. So this seems to give you a reason to expect the existence of cosmological islands. Because if you want to compute the entanglement entropy of a large region of your 4D CFT excited state, then what you have to do, and you want to compute it holographically, what you have to do is to take the corresponding region in the effective theory in the bath and then allow the existence of islands in the cosmology. And in fact, obviously, this is exactly the same analysis as Harman and collaborators. So this tells you that you definitely get, if you take a large enough region of the bath, you definitely get an island in the cosmology. Okay, so this is just a quick summary. A takeaway from this talk is that if you have these Euclidean ideas for wormholes that are due to these confining theories built up of two 3D CFTs coupled by a 4D CFT, then you can slice open the corresponding path integral into different ways. One way you get these symmetric cosmologies, and they're encoded in a very, very complicated way in this 4D CFT excited state. Or you can slice the path integral open in a different way to get a planar wormhole. And this is encoded in a much simpler way, just more like ordinary CFT in the vacuum state of this Lorentzian confining theory. But the two pictures are related to each other by double 90 continuation, by this slicing duality, meaning that cosmology in these ADS-CFT settings is dual in this precise sense that we described in this talk to the vacuum physics of confining theories. So I'll just mention a few open questions. One of them is, so far we have a semi-bottom-up approach in the sense that we have an idea what the microscopic dual should look like, but we don't have a specific example of two 3D superconformal field theories for this set of degrees of freedom coupling them that give rise to a specific theory. So this would be something very interesting to study, because once you fix that microscopic setup, you get an answer of what your cosmology is. And so that's definitely something we would like to understand soon in the future. Another question is the one related to the accelerated expansion, which is the first step to get a realistic cosmology. So can you get, can you have a potential for a scalar field or multiple scalar fields that gives you accelerated expansion, preserves the existence of the wormhole, and respects the BF bound? This is another interesting question, is whether or not we need primordial inflation. Now, it seems like we can solve many paradoxes that inflation solves without inflation, but of course, inflation also gives you a lot of nice predictions about cosmological perturbations. So for example, the scaling variance of the perturbations is CMD that are explained very, very well by using inflation. So the question is, maybe we actually need inflation also in our models to get those kind of predictions. And being ordinary, some sense an ordinary cosmological models, we can embed inflation in these scenarios, just like we can embed a late phase of accelerated expansion. And cosmological perturbations is actually a very interesting open question in the sense that given these models, we should be able to study cosmological perturbations in them. Starting even from the wormhole, just look at what the spectrum of the perturbations will look like in these models. So that's something that we want to do soon. And finally, of course, the far-fetched goal is try and understand if these cosmologies can match observational data. So if given some microscopic example of these cosmologies, that example could actually lead to something that looks like our universe. And so this is certainly another open question. This is all I have. I'd be happy to take questions.
So your models only describe cosmologies with time-symmetric slices, correct?
Sorry, you couldn't hear very well.
You only have time-symmetric cosmologies
Yes.
in your models, so you can't describe multiverse type models or anything like that.
No, these models are inherently symmetric.
I see. Second question was, can you at least in principle describe the physics arbitrarily close to a singularity, so a Big Bang in your setup?
Sorry, can you repeat that?
Can you at least in principle describe the physics arbitrarily close to the Big Bang?
Well, that's a good question. Not using effective field theory, sure, because at that point, of course, all these effective field theories I've been talking about break down when you get too close to the singularity, very high curvatures. So using effective field theory, no, but in principle, have a microscopic example, then that microscopic example should describe the AUV complete theory of quantum gravity, right? That's exactly the point. You want to study quantum cosmology. So if you have an explicit example of these microscopic theories, then certainly you can have a description of the whole evolution. Now, what that singularity will look like, that's a very good question. We might not have just a simple FRW kind of cosmologies. We certainly don't have that because quantum gravity correction would kick in. So in principle, using these models, if we find explicit microscopic examples, the answer is yes, it could tell us what happens when you go all the way close to the singularity. But for sure, effective field theory will break down.
When you reconstruct this wormhole, this static geometry using these two scalar fields, the spectrum of those scalar fields, are they part of the interface theory, or they are at the boundary of the, when you couple the 3D CFTs?
So where, sorry, can you repeat, where do you define the two
When
CFTs?
you reconstruct the wormhole, the static wormhole geometry using these scalar fields, are those scalar fields part of the spectrum of the interface theory that you were describing, or is a different thing?
So, sorry, can you pull down your mask? I couldn't really understand. Okay.
When you reconstruct this wormhole using these two scalar fields, the spectrum of these two scalar fields, are those part of the spectrum of the interface field theory that you were describing, or is it a different thing?
No. So what I'm saying there is that if you, I didn't go into much detail in that. The idea you're talking about what I mentioned, I guess, in this slide. So the idea there is that if you take a traversable wormhole geometry and you just consider a test scalar field in this traversable wormhole geometry, then when you quantize the scalar field, since it's like putting a scalar field in a box, you get a discrete set of modes. And that discrete set of modes correspond to a spectrum of massive particles in the dual confining theory. So in the corresponding microscopic theory given by the 3D CFTs coupled by the 4D CFT, you get a spectrum of massive particles, just because it's basically the spectrum of confinement of that theory. So no, it doesn't have to do with those interface branes I was talking about, but it's just a feature of a Boole theory that has a traversable wormhole.
But then wouldn't you need like non-local coupling between the two CFTs?
No, in this case, we don't have a local coupling. The coupling is given by these additional degrees of freedom that are 4-dimensional on an interval that couple the two 3-dimensional CFTs at the ends of the interval.
Okay.
So you don't have an explicit coupling, which also introduces UV divergences and lots of other problems.
Thank you.
So in this plot, I find it surprising that you have this non-monotonic behavior, this bulge in the center. So aren't you worried about the city violating a C theorem?
By what? Sorry.
Aren't you worried that this violates some C theorem? Like it seems that
No, that's why I said in the beginning. In the beginning, what I said is this scale factor doesn't have any physical meaning. This just we picked the form of the scale factor explicitly and then quantize a scalar field in it. And the reason why we did that is that we just wanted a scale factor that was simple enough, that was not computationally expensive to reconstruct, and it also had a non-trivial shape such that we could observe very well whether or not the reconstruction was working. But this specific scale factor does not have any physical meaning. So yeah, but you can do it with a monotonic scale factor, it's no problem. Actually, it's easier. But we just wanted to check that whatever scale factor you put in, once you quantize a field, get the corresponding spectrum, you can reconstruct it. Thank you.